At this point, we already had gone through a lot of material concerning consumption data. We understood what consumption data is, what it means. We specifically look at geolocation data as an example for consumption data type. And we went through a series of lab exercises that allowed us actually to work with this type of data. So the question that is left to be answered is what we could do with this type of data in terms of our work as financial professionals. So based on research that I've done with my colleagues, I want to present to you some applications of how to use data that is derived from consumption to predict certain variables in the financial markets. In this particular example, we're actually following about 50 retail companies, and we try to derive consumption proxies through using some of the techniques that we saw before. The data actually covers information from 2009 to about 2014, and later on we'll update, in the next application, we'll update it further to 2017. Although the sample is relatively small in terms of number of companies, only 50, they actually represent a very large part of the overall retail consumption in the United States, about 64%. So again, the idea is to learn about the economy and about specific companies through information that comes from alternative data related to consumption. We call them here consumption proxies. One of the examples is a set of mobile devices from which we draw information. In this case, we look at information that derived from a subset of Android devices, and we try to figure out what people actually intend to consume in GAP. And we have another example that looks at the larger sets of events. Well, if you just look at the GAP example, you see patterns that are related to what we understand about consumption. There's typically more consumption around the end of the year and the beginning of the year, and then spikes in the middle of the years that correspond to some promotion arriving at the summer. Let's talk about the design of this research. Well, each company goes through a cycle. They start the fiscal quarter. We call it here point 1. They end the fiscal quarter. We call it here point 2. And then they take some time to report the results, the performance they had during the quarter. A few weeks post-quarter end, we call it here point 3. What we'll try to understand is whether we can use consumption data, consumption proxy, to figure out what was going on during the quarter for each one of the firms in the sample, so as to predict their performance before they announce it. So we collect the data from our sets of alternative data. We aggregate the data per company and over time, and we derive a measure which we call CA, consumption activity, per each one of the firms. We then appreciate that companies go through seasonal effects, and then we correct this measure of consumption activity by the season, and we call this new measure that we develop RTCS, which stands for real-time corporate sales. So this measure actually allows us to capture what we think is the best proxy for what the company actually sees in real time in terms of the sales activity. So the first question is, well, does this measure correlate with actual sales? That's what it intends to capture. Well, we capture this information throughout the quarter, and then we wait for the company to actually release their revenue numbers a few weeks after that. In hindsight, we look at the correlation between what we were able to measure in real time and what the company actually released, and we find very high correlation, which is a good verification for the quality of the data. Well, the next thing is to see whether this information is actually predictive. whether we could have used this information to predict corporate surprises, for example, earnings surprises. And in fact, we see that that's the case. As we can see in the table, we're able to generate, using this information that was measured within the quarter, we're able to predict the surprising in earning that would be released in 3 weeks or 4 weeks' time when the company actually released the numbers. The next question is not about predicting earnings surprises, but it's actually seeing whether we can profit from this ability to predict earnings surprises. So we divide the universe of firms to 5 groups based on how strong this measure that we're able to extract is. And we see whether there's a difference between the low group, the group with the lowest consumption activity, to the highest. And in fact, we see, as you can see in the table, that companies that we were able to measure for high economic activity overperform companies for which we measure low economic activity. We can then look at whether we are doing better or the information is more predictive of positive surprises or negative surprises, and we see that it's pretty balanced. Therefore, we are able to establish the fact that first, consumption information is reflective of what is actually going on inside companies, and second, that it allows us to predict returns and earnings surprises of corporate earnings. In the previous section, we focused on consumption data, or at least our best way to estimate consumption, from the beginning of the quarter, that's point 1, to the end of the quarter, that is point 2. In this section, we'll focus on what happens, or at least what are able to estimate about consumption from alternative data from point 2, that is the end of the quarter, and point 3, that's the time that actually takes for the company to issue the earning announcement for the quarter. The reason it's interesting to focus on that separately is because when earning announcement actually come out at point 3, they do not have to include information of what happened after quarter end. It could be communicated by managers, but they don't have to. So we can ask many interesting questions. For example, we can ask whether manager withhold private information. Well, using the alternative data, the consumption data, we can estimate what the manager really see about the economic activity that happens within the company between quarter end and the announcement, but we don't know whether they're communicated to the market. Well, it's easy to test whether they will communicate it or they are communicated this information or not. That by looking at post-announcement return. That's what happened to the stock price following the announcement and to the next quarter end. The reason we can look at that is because if the information was disclosed, all the information that available for the managers was disclosed in the earning announcement, we'd expect this variable that we call PQS, this is the variable that estimates the activity from the end of the quarter to the announcement, to be insignificant. However, if the variable is significant, it tells us there's something about the management disclosure that did not go through, because otherwise it would not be significant. When we observe the results, we actually see that information that is estimated by consumption data from quarter end to the announcement is actually positively correlated with the return of the stocks following the announcement and to the future, which means that management withheld information from the market. So now we have another question to ask. If management indeed withheld information, can we actually say something about the disclosure that they actually made? And that we can do easily using regression analysis. Again, we use the PQS. That's the variable that estimates the consumption from quarter end and to the announcement. And then we observe the return of the stock during the earning announcement. If this variable is either positive or negative, it can tell us something about the quality of information that the management disclosed. We observe this information using regression analysis, and we see that it's highly negatively correlated with the stock return during earning announcement. And what does it tell us? It tells us that managers actually had access to information which seems positive. That's PQS positive. However, the stock price actually dropped, which is questionable. What is happening here? Well, what could be happening is that management released to the marketing negative information which impacted the stock price negatively, even though PQS had been positive. What are the channels by which management can convey this information to the market? Well, they can change the guidance. In this case, reducing the guidance, even though they see positive information. Or they can communicate the sentiment, the tone can change when they discuss the earnings in the earnings call with analysts and other meetings. So we tested the management tone using during the announcement, and we compare it to PQS. And we actually see something very interesting indeed, that PQS is negatively correlated with the tone of the management. The more positive the information that is coming out following quarter end and through the announcement, the more negative the tone, the more pessimistic management a tone sounds. Which obviously begs an interesting question. Well, what do we know so far? We know that PQS is negatively related with announcement returns, but is positively correlated with post-announcement returns. So what are the options here? Is it possible that managers affect prices for personal benefit? They know that information is about to come, which is very positive. They talk down the stock, the price fall, and then they purchase stocks to their own account. Well, we can actually answer this question, at least to some extent, or to some degree of confidence, and that's by reviewing the buys and sell of insiders in the company. And we model it in a regression sense. We add a variable which measure whether management were net buyers or net sellers of their own equity following the announcement. And what we find is highly significant results, which are consistent with the notion that management indeed observe positive information, talk down the stock price during the announcement, the price indeed falls, and they take advantage and buy their stock, experiencing a positive return in their own account. In the previous sections, we looked at information about consumption which is derived from proxies of foot traffic. These proxies estimate the flow of people to the stores, but they only deal with retail stores where people actually go physically to shop at. Well, this is obviously very limiting, because first, the sample size of companies for which we can gather good information is very small. And second, the economy as a whole is transitioning from physical buying and shopping in the store to online shopping and interactions over the internet. So what we've done in this paper, my colleague and I, are two things. First, we extended the sources of information from the retail activity that's done on foot, that's the initial data sets. We increased it to include now also information about web traffic related to e-commerce transactions and interaction of consumers with brands. That actually allowed us to increase the sample from about 50 firms to more than 300, to cover a lot more of the economic activity in the United States, and actually answer questions which are relevant to the speed by which each type of information type is disseminated to the market and to the asset prices. We also extended the sample from 2014 at the previous analysis to 2017. So we're looking at 9 years of data now, which is much more meaningful and allows us to get more insight and more statistical inference quality. We're looking again at 331 firms. 178 of those firms are consumer-facing or companies within consumer sectors. So we have 3 proxies for consumer activity. One is related to foot traffic, the same way we did before. One is related to consumer interaction with different brands. And the third one is related to the web traffic, which is relevant to the e-commerce transaction people do on certain websites. The first questions would be asking is whether this information that we're gathering is related to the fundamentals of the companies. That is, for example, whether the information gathered is related to the actual sales number that the company would be announcing at the end of the quarter. Again, we measure these proxies throughout the quarter and then wait for the announcement following quarter end to see if they're correlated with what we measured. What we see is that both the in-store proxies, the brand proxies, and the web traffic proxies are highly correlated with sales. Second, we're going to ask whether the information that we're gathering is related to things that people don't know about the company. So whether there's information in addition to what the market is pricing. And the way we do it is very simple. We're going to look at what analysts forecasted for earnings for each one of the companies before earning announcement. We'll wait for the earning announcement to see what the numbers really were. We look at the difference between what the number were and what the forecast had been. The difference between these two numbers is the unexpected, is the surprise in earnings above what the analyst expected. Now we're going to regress these numbers on the variable of interest, on the in-store proxies, on the brand proxies, and the web traffic proxies, and to see whether these numbers are able to predict not only the sales, but actually the surprise in the market. And what we see that this indeed happens. This information that we were gathering from consumption numbers, from the alternative data, was able to predict not only the sales, but actually was able to predict the surprise relative to analysts. Finally, we're going to ask ourselves, can we use this information not only to predict surprises, but actually to benefit in terms of our predictions of return? So what we've done something very simple. Each quarter, we split the companies to 5 groups, 5 portfolios, from the worst performing in terms of our proxies to the best performing in terms of our proxies. And then we measure, on average, how the positive group did relative to the negative group. What we see is something very nice, which is that on the positive side, each one of these proxies is able to predict positively earning announcement return. On the negative side, the picture is a bit more complex. We see that in-store is definitely predicting negative, brand is predicting negative, and there are some mixed results in the web transaction. So the next question we're going to ask is how quickly the information about each one of these processes is disseminated to the market. And the way we'll do that is by measuring the within quarter transaction proxies, and we see whether they are starting to influence the price even before earning announcement. And what we see there is that only happens with the web proxies, which means that probably information that is gathered from the web is available faster to market participants compared to the in-store transactions and the brand transaction. So in sum, we were able to extend the sample from 50 firms to more than 300. We've been able to cover a lot more for the economy than just the retailers that people go physically to the stores by extending it to brands and web transactions. And then we're able to gather good information about the speed in which information is disseminated to market participants. Textual analysis is used in many fields. Take document classification as an example. Think about companies getting complaints through the Twitter feed or through the website and need to direct it to the right person in the organization that know exactly how to process a specific type of complaint. Textual analysis would then be helpful to classify this piece of information and direct it to the right person. Directing emails incoming to the organization would be following the same process. Search engines are another example of information retrieval using textual analysis. Both of these methods and these examples are heavily using textual analysis, the same fundamental tools that we'll study in the next few sessions. But our focus is the financial market. We want to use textual analysis to treat information that we bring from the open web such that we can use it to predict financial market variables and behavior. We will try to use textual analysis on open web type of data to measure things like risk and uncertainty. Even specifically, we'll try to measure legal risk through processing of specific pieces of text. We'll try to predict asset prices using textual analysis. And even in one of our labs, we'll use an alternative definition of industry and sector classification using the toolkit of textual analysis. During this program so far, you acquired a lot of analytical tools, mostly applied on numerical data. Here we're focusing on textual data. Text analysis and numerical data analytics are not fundamentally different. Many methods are applied similarly. However, textual data is very different from numerical data. So why is textual data different from numerical data? First, it's unstructured. Before reading a piece of text, you actually don't know how long it's going to be, how many words are going to be mentioned in the text. Whereas in numerical data, you pretty much know at least the format of the data you're going to be receiving and processing. While textual data has other issues that has to be dealt with. There are misspellings, for example. Some people use abbreviations where other people don't. There are different styles of writing and processing text. There's different punctuations. Some people use synonyms different ways than other people. There's specific terminology that is used in some documents and might not used in others. And there's also the case of the context. some word would mean one thing in one context, but another thing in a different context. In the next session, we will learn how to process textual content, taking into account some of the problems that we just talked about.
Web scraping is an extremely powerful tool when it comes to data collection. When you see all this information on the web, it's tempting to copy-paste things down, to take maybe charts offline, all these different things. But it can become very tedious when you keep needing to pull the same data and putting it in the same kind of format. What web scraping allows us to do is programmatically pull down this data and bring it into whatever form we need. The first thing we need to go over is what exactly request in Beautiful Soup is. Now, request is the way we're actually pulling the data. So we'll say, here's a link. For example, this is the Wikipedia page for the S&P 100, which I have over here. Now, we want this table right here. That's our goal of web scraping. Every, let's say, month or two, we're expecting that this table could potentially change, and we want to every month pull it down so that we have a running list of the S&P 100. And we don't have to constantly have some poor analyst pulling it down every day. So first we use request, and request pulls down the actual web page. Now Beautiful Soup, what its job is it's actually parsing the data. So it's taking this request for this web page and turning it into an HTML representation that we can easily query and work with. So right here, this prettify function, this is what will actually make it look presentable to you. So you can see it actually breaks it down into all these different tags and makes it very easy for viewing. Now let's talk about how you actually query the data with Beautiful Soup. The first thing you can do is do find. Now find looks for the element and returns it. So if you were to say find title, it will return the title. So the S&P 100 Wikipedia. That's this title that I got from all the way up here. As you can see, the title. And it will do that automatically. And maybe that seems really simple for now, but you'll see where the nuance comes in. We don't have to actually search for only one thing, though. We could say, let's find all tables. Maybe that there's going to be a variable number of tables in one of these web pages, and you just want to pull down everything just in case, one day there's 5 tables, the next day there's 10 tables. You want everything pulled down no matter what. So find all tables. You can see that there's 4 tables, and you could go through the first one, and you'll see this one says the class, it says all these different things. And it's kind of hard to read right now because there's so much, but we'll see how we eventually reduce it down into whatever data we actually need. An option when working with this is you can actually pass in a dictionary of things that need to match. So you say table, but the class has to be sortable. And the reason we might do this is we know there's only a certain number of sortable tables, and that's what we're looking for. Everything else can be left behind. So the reason we have sortable here, if we go to inspect, and now this tool right here in Chrome, it allows you to actually inspect the web page and look for these different tags and the different information that we need. If you go up here, you'll see, here's the table and it says class. One of the classes is sortable. So this is very effective. Going in with Chrome, using this inspect tool and going through and finding distinctive characteristics of what you need to pull. So for our purposes, we know that this sortable table is what we're actually going to pull. So we want to look for the distinctive characteristics so that no matter what changes, if there's something new, we can easily identify it each time with our programming. Now let's go back. So there's 2 in this case, so we can't actually just do that. We're going to have to actually be a little more nuanced. But for now, let's actually start to look at some of the attributes. So if we have our example table, that's the sortable table, the first element. Attributes will return back all the attributes. So here's class, and we can see wiki table and sortable. We could also just pull in put the actual key class in there and get back that exact same thing, and we'll get wiki table sortable. Another example of something we can do If we do .text, it will return just the text within that element. So if we have an entire table, it's going to return all of this. Now that might not be what you want, and it's kind of hard to read. If we were to actually do, let's say, a certain paragraph element, then it would be a lot less text because we would only get the text in between the elements we were looking at. Now, we can say, is there a way to identify this table, this S&P 100 table, by the class? But if we do that, we see the two tables both have the same classes, so we can't use class to identify. But what if we know that there's a certain word? Now, this isn't a perfect example because Apple may not always be in the S&P 100, but for now we'll start with this, just as an example. Let's say the word Apple Inc. we're sure is in the S&P 100 table. We say find all where the text is equal to apple.inc. Now, this print.elements, it's going to return the element, but you'll see it's not the entire table, it's just the small element that contains it actually. We can also say assert the length of this is 1, and this is just a check for us to ensure that we're not accidentally pulling multiple pieces of elements where the text is apple.inc. If we pull multiple, maybe we've done the wrong kind of characterization, and we want to go back and look and see how we can identify better. Now, we have our element. So we'll say, what's the type? And you see it's navigatable string. It looks like we have a string, but we don't actually. It's a little bit different. So it has a few elements to it that a string wouldn't have. Parent will go up, and it will give us whatever is on top of it, whatever is encasing this element. So here, we see what's encasing it is actually a hyperlink. So great. Now we know that there's actually a hyperlink after this apple link. But what exactly can we get if we go again up? If you do it again, now we get the actual column. So you see this TD. Once again, if we did it, we do the third parent, we get the row. Now we see that the row it's in. So I'm just going to pull over here. Essentially, what we're doing, we're starting here, this A, then we're going up to the TD, then we're going up to the TR, and eventually, we'll go up to the T body. You see what I mean. We're just keep going upwards and upwards of the parents, figuring out what's above it. Finally, we get the body of the table. Now, that's what we have. We could also say something like this. Our Apple element, find the parent that has a certain tag. And that will skip doing parent, doing that over and over again that we see before. And this will return the same thing, this T body, the table body. So from there, it's very easy. We can find all the rows. We have our table, that element, which is the parent, the third parent or the T body parent of our apple.inc. And now we say find all TR. That's find all the rows. And we'll see the length of these. It's 102. We can print 0 and we can print 1. So we can print the first and the second element. And you see the first element has nothing good for us. It's symbol and name. It's just the headers. We don't need that. Then that second element, we actually have the name of the company and the hyperlink to it. So we could also just do this. Maybe we want to find the hyperlink for each of these S&P 100 companies. And the reason we're going to do this is because for our next section, we actually want to get all the different company web pages, or Wikipedia pages, and we're going to get the textual analysis from there. So now we say, for the table, find all of the hyperlinks. So we say the length of the links, we have 101, and you can see here's an example of one of those links. If we do attributes again, this time we actually see there's href. And this is the link to the page. And this is very important because this is how we're actually going to get to the different pages. So let's make sure we take that out. So let's take our links list and let's just apply a list comprehension and take out all of the hyperlinks. And now you see we have them in this form. So something else that's very interesting, there's a potential for there to be two shared classes, a class A, a class B, and this can cause some issues. So we want to check for duplicates here, and that's what we're going to do. So first we say numpy.unique, and we're going to give it links, and we say return counts is equal to true, and what this will do is it will return each unique element and the number of times it appears. As you can see, there's one element that has two. So we're in trouble. We can't actually have repeated elements. We need to deal with it first. Now we can say, let's find the index of wherever these link counts are greater than 1. And if we were to index by that, then we see Alphabet has 2 share classes. So let's go back. And you can see this is our list. And if we were to go, we see Alphabet Inc. A, Alphabet Inc. C. And this is an important part of the data cleaning process, understanding that there's these kind of very minor things that we need to deal with. Now, we have the hyperlinks, but we need to actually add this prefix to it for it to actually work. So now we add this Wikipedia prefix, and now we have all the new links. So let's try pulling text from each page. So if we were to actually do this, you can see we go here, and this is what the page looks like, each page for the company. And we can grab all the text data within paragraphs. So we say, for this web page, find every single P, find every single paragraph, and then we're going to take the text for every single paragraph. So now you can see these. Something else, if you recall, we can easily join things together with the delimiter like this. Give it a string, which is the delimiter, so in this case it's a dash, and then join a list of elements. For us, what we want this for, we're going to take all those paragraphs we just had, we're going to have the delimiter be a space, and we're going to join every single paragraph so we can very easily just look at all of this. And now you see for a one page for this 3M, we have an entire corpus now of text. And we'll do this for each individual company, and then we'll have the entire text of the Wikipedia page that we're looking at for each company. To do is actually clean it. You see, when we look at this data, we might see these numbers with brackets. And to Wikipedia, what this does is it signifies where we get our sources from. And now this is great on the web page if you want to actually see the source of some of this information. But for our textual analysis, these bracketed numbers actually don't add any value. So we want to get rid of them. But we don't want to do the manual task of deleting each individual one. That would be a long time and waste of time, honestly. So what we're going to try and do is learn about regular expressions and how they can be used to identify textual patterns, and then later, how the textual patterns can be changed easily. Now, we have, let's say, OU. This string appears 3 times in our text. So the regular expression library find all, if we were to give it OU, it's going to return 3 instances. But this isn't very helpful. What's helpful is you can actually start to look for patterns. So let's say we want to say, find everything that has OU and then has letters A to Z, lowercase. If you do find all, OU, A to Z, what's going to come out is our and out. So now we can actually see a couple different variations of words that starts with OU and then have lowercase letters. Likewise, maybe we're only interested in the word, letters A to R. If we do AR in the brackets in the regular expression, we end up getting our. So these brackets are a way to basically say we want a certain type of character. So A to Z, we want letters lowercase. A to R, we want lowercase letters A to R. We can also extend it even more. Before we had A to Z lowercase, if we do A to Z and then uppercase A to Z, we want any sorts of strings where we have either the lowercase or the uppercase, any letters A to Z. And you'll see we get our, out, we get our that has this capitalized R at the end. Another very important function of regular expressions is that we can actually split text based on it. So maybe you wanted to see every single section where there's an annotation. Well, for this example, we're not going to look at the annotations just yet. That's eventually what we're going to get to. But if we wanted to say any place where we had OU followed by any letter, and we want to split the text into pieces, we could do that. So now we have this is, test string defined, and so on. re.sub is the way that we can actually take any sort of matched regular expression and we can get rid of it. So let's say that there's sensitive information and we want to look through a maybe 200-page document and replace it. We can very easily find the sensitive information, and maybe we're afraid about lowercase letters, uppercase letters, something along those lines. We can find those and replace them with redacted like we did here. Now let's begin to move on to the actual numbers that we want to replace, these bracketed numbers. So if we were to do find all 1 to 9, it would return all the one-digit numbers. So we get 1, 2, 3, 3. So the thing is, though, if you look up here, this is actually 33. This isn't it isn't two representations of the number 3, it's the number 33. So this is where we need to be very careful when we're creating these expressions. If we were to actually replace with x, you would see we'd replace and we get x, x, and then xx, because each of these numbers is being replaced once. But when we have 33, it's being split into 3 and 3 and being replaced with x and x. Another thing we can add on is we can actually have this plus. So what this plus does in the regular expressions is it says we can have one or more. And this is very important because when we go 1 to 9, we're saying any numbers 1 to 9, but it's one or more occurrences. So now we have 1, 2, 33. So now we actually break out 33 into its own number, which is very important. Something else that we need to be very cognizant of is you can't actually search for these brackets without using the escape character over here. The reason for that is that these brackets are what regular expressions use to denote kind of patterns. So if we want to say, like, as we did before, A to Z. What we're doing here with the escape character is we say we actually want the bracket. So as you can see, we get the left brackets, we get the right brackets. Now if we bring them all together and do any numbers 1 to 9, 1 or more, and then we do the brackets on the outside, we can actually isolate right here the occurrences where we have these brackets with numbers in between. Finally, we can sub out like this, and now we've gotten rid of them, which is great. So for example, let's take the first 400 characters of these paragraphs. Now, we have the annotations, these numbers in the brackets. We take our regular expression and we substitute out any of these with blank spaces, and now we've gotten rid of them. So when we go for eventual textual analysis, we won't have to worry about them messing up results, because when we're looking at companies, it doesn't really tell us much if one company has bracket 3 end bracket and the other one does too. It's just leading to the footnotes where the sources came from. So now we can do it on all the paragraphs we want. And now we move into even more kinds of data cleaning we can do. Now, when we have textual data, a lot of times there are words that essentially mean the same things but are different variations. So let's say run and running. The basic idea is that you're doing the exercise, you're running. But at the same time, you might see run and running, and the textual analysis won't differentiate, or will differentiate between the two unless you use stemming. So stemming will break run and running down into the same word, run, because that's the basic idea. Snowball Stemmer from NLTK, the library, what this does is automatically applies all of these stemmings for every single word. And it's very helpful for reducing the amount of noise in the data. So now we have the paragraphs after being stemmed. Count vectorizer from sklearn, this is the technique that we can use for getting the counts of all these words. So now that we have done some data cleaning, we feel good about the data, we need to actually transform it into a matrix of word counts. So now if you were to just do it the regular way, this fit transform will return to you not something that's readable, it's a sparse matrix, and we can't really use that right now. It maybe in the for other people it's much more efficient on memory, but for our purposes, we're going to want to actually see the words for now. If you were to do counts to array, that's going to return the counts of each individual word. But now you're probably asking, where are the feature names? What are the actual words? And we get that from the vectorizer get feature names. So we see analysis, analyze text dat too. So now we have both the counts and the names, and we can combine them into a series, and we can actually see the different word counts. Now, you might also be asking, are all these words helpful? We and with, these kinds of words happen everywhere. It's not necessarily that it's very predictive for a specific Wikipedia page for a specific company. The word we is universal, so we want to kind of get rid of some of these more common words that don't really add much value either. And that's what stop words are. If we tell our count vectorizer to use stop words in English, take out any English stop words, what will end up happening is it will get rid of all of these words for us that don't add any value. So now you see we reduce all of these down to just these 4 words: analysis, analyze, text, and want. So this will reduce the dimensions, both making it potentially less noisy data, but also more efficient. So now we want to turn this into an actual function. And what we're doing here is trying to make it so that we can do this for every single company now. We've only looked at one set of data, but now we'll make it a function so that we can, in the future, easily look at all the different company counts of words. And then we just extend it to be multiple companies. So now when we do this, if we were to say counts is equal to in the first 2 links, now we get back a matrix of the word counts. Now we also want to say what the index is, what the company name is. Now if we take, after the 30-second character and all the unique links, we end up getting what each of the company names are from that. And this is very helpful because then we can actually identify. We're not using 0, 1, 2, 3, 4. We're actually going to have some context. So this is going to be how we get the index. So we're going to run again, except now we're going to say the columns is equal to the index. And now we have these counts, where we have all these different companies and we have the different counts of the words. We can save down the data for future use, and then go and find the most common words. So not surprisingly, company is the most common word. It makes sense given all of these are companies. And we can also see things like bank, United States, business. And this is an important point, this United States. Right now we're looking at a very basic example. But if you extend this textual analysis, you will want to start looking at United States as one word. When you're doing these basic examples, you can split everything into each a word. But there's context to United and States being right next to each other. So this is something that in the future you can extend and create a much better data set from. But for now, we'll just look at one word at a time. We can also convert this to word frequency. This is important because we don't want document length to kind of bias some of these differences. We want to see what the frequency is for each of these different words. Next time, we're going to go through company distances, and we'll begin to look at how these matrices of word frequencies can actually be used to identify which companies, based on text, are most similar or most dissimilar to one another. Similarity is to look for the distance between vectors and matrices. Now, when we're looking at these textual matrices, what we're going to try and see is one company, their word counts, versus another company's word counts. And we might try and do some sorts of normalization, such as what we've done before, which is taking the frequency instead of just the nominal number. And this is to adjust for the length, because we don't want to bias certain documents. Now, when we're looking at distance, we can use a very basic Euclidean distance. Now, there's a lot of different distance formulas that people use, but for now, we'll start with just Euclidean. So if you see here, what we're doing is we're looking at the differences, and we're squaring them, and we add up all these squared differences, and then we're taking the square root. So just your basic Euclidean distance. And it's easily applied on any 2 companies. So for example, we take the word frequency of BNY Mellon and the word frequency of JP Morgan. And when we look at the distance, we see it's 0.069. Now, if we were to do it with Facebook in BNY Mellon, we actually see a much larger distance, 0.094. Now this distance represents the fact that JP Morgan and BNY Mellon have much more word frequencies in common rather than Facebook and BNY Mellon, and this is something we would expect. Now, it's obvious when we look at it here, but what happens is once we get to data sets of thousands of companies, it becomes a little more nuanced. It's tougher to just say the obvious that, you know, two banks are going to be similar. So the reason that we really want to develop this now is so that we can apply it to large data sets where we don't have to use as much human insight. We can kind of apply these heuristics, such as the distance being what we're looking for. Now, the first thing that we're going to do is remind you how itertools works. Now, itertools is an important library that will let you make combinations. So the reason that we want to do this is because we want to see each individual combination of a company, and we want to find that distance. So let's say, you know, 3M and AT&T, 3M and AbbVie, and what combinations we'll give back is a list of every single combination that's possible of all these companies. And we're going to be looking for the pairwise distance when we do this. And that's going to tell us which companies are most similar to one another and which ones are most dissimilar. With the combinations in mind, we'll turn it into a data frame by giving the list of combinations to pd.data frame. Now we have company 1 and company 2 representing the names of the companies, and we can get the distance by applying a formula, find distance, for each company 1 and company 2. As you can see, we got out the different distances. So 3M and AT&T, 3M and AbbVie, and we can get all the way down every single one now. You'll notice it's a pretty big matrix because, you know, we're looking at a lot of different companies. So there's a lot of pairwise combinations, and this is one of the issues when you start thinking about high data, big data issues, because all of a sudden you might have thousands and thousands of companies. So when you go to make, the pairwise distances, you might start needing to use some of the big data techniques. But for now, at least the data set's manageable. We can do it in here. Sorting by distance, we can see which ones are most similar. So you'll see interesting Citigroup and JP Morgan Chase. I think it makes a lot of sense, two banks. You see MasterCard and Visa, very, very similar business models. So we can kind of see down. Something else we'll do just for convenience is we'll actually take the exact same data frame and we're going to mirror it. So that's because company 1 and company 2, when we did itertools, if we had company A and company B, we'd only get the combination AB. We also just want to show BA for any sorts of pivot tables or anything like that. So we're just going to copy it over and then flip it and then concat the two together, and that's our new distance table. So it's exactly just the mirror. And now we can look at specific companies. Let's say Wells Fargo. We want to say only where company 1 is equal to Wells Fargo, what are the closest companies and what are the farthest companies? So you do Wells Fargo and you see Citigroup, AT&T, JP Morgan, Procter & Gamble, Goldman Sachs, Caterpillar, Bank of America. So you see a lot of banks, and this is maybe hinting towards industry classifications can be very useful for this being very similar to textual data. But also we might say an industry classification might not be the most accurate. We actually want to take this textual data and use that to enhance our industry classifications. Because all the time, these industry classifications, they're changing. We might have conglomerates acting in multiple different industries. And we might be more interested in what the text has to say about what companies are really most similar, not just these industry classifications that are in some ways a little bit subjective sometimes. Now, to get the industry classification, we're going to also do some web scraping again. So if you see right here, what we're going for is the table with the class info box. And that is this one right here. And it's just an info box with all sorts of data on the company. Going back, we see it's a lot of data, but we can make it much easier. We just need to find the header row with the text industry. So as you can see right here, that's our header row. With that, we'll say get the parent. So we want to get the outside element that's containing it. And now we can very easily say return the array of all the different titles. So for this first company, all we get is conglomerate. And we're going to say, take the text from this for all the hyperlinks within this industries table. So this first one, we get conglomerate. Now, we'll make a function that then gets the industry classifications for multiple companies. When we're doing this, it's the same exact idea. We're taking that text box that has industry, and we're going to say, find all the hyperlinks out. When we do that, we see conglomerate, telecommunications, technology, mass media, and entertainment. So that's one list, and that is, for just one company, there's 4 different industry classifications. If you look back on Amazon, you'll see a similar thing: cloud computing, artificial intelligence, consumer electronics. And the point here is that at first you might make this web scraping. You would look and you just take the first industry. But that's not good enough. You need to really look at the data and make sure, are you missing something? And in the case of this, if you just did it only on the first example, you would say conglomerate. If you were to do it on, let's say, Amazon, you would say cloud computing, but maybe you go back and you say, that's not totally fair. It's in multiple industries. I want to actually pull each individual industry in there so that's a full representation. So that's just something to keep in mind. And now we're going to actually make a data frame with dummy variables. So we'll have 0 represent if a certain company is within that industry. If it has that, if it's the list of industries that it's associated with, it's one of these. So let's say conglomerate. It's 1 if this first company is in it. Telecommunications, technology, mass media. This second company, it's in all of those, so we have 1s there. And so we're just making a 0, 1, maybe even you could say a Boolean index on which sectors are represented by which companies. So now we'll just kind of clean it up with a function. We'll actually pull it in, and now we have all the different companies and all of the classifications that they are technically in. So you have 3M, you're in a conglomerate. You have AT&T, you're in telecommunications. We'll also say which industries are most common. So when we do this, we're summing up, and we're going to say sort by values ascending equals false, so we get the top values. And you see financial services, you see conglomerate, you see retail, you see a lot of different things. But something interesting here, financial services you see again. And now why might that be? So the real world data is messy, and all of the time you see things like this. Capitalization matters, so what we're going to do is we're actually going to just lowercase everything. We're going to go back and say, we don't want to accidentally pull financial services capital and financial services lowercase as 2 separate entities. They should be the same thing. They mean the same thing. So then we're going to go and we revise and we add this lower to the industry classification to lowercase everything so that we don't run into these issues. Once we have that, we have a new matrix. And now it's corrected. So you see financial services has 16 now. It's a much better way to do it using this lowercase. And generally speaking, that's a good idea when you're looking at some of these string data. If the capitalization actually doesn't add anything, a lot of times it's probably just the best case to lowercase everything, just to be safe. Of course, that's saying unless the capitalization actually means something, and then it's a little different. We'll also just filter out any industries where there's less than 2 representative companies. And we'll do this because we don't really want to compare where it's only 1 as the comparison base, because it'll kind of skew the results a little too much. And now 2 is by no means the exact best number, but in our case we have a very small data set, just the S&P 100, so we don't really want to cut out too much of our data. In your future expectation, your future tries of doing this, you might necessarily want to have a much higher level, just to make sure you say, let's say, 10, 50 companies first are in an industry, so that you don't have the small sample bias. Now let's look at this. What companies are in financial services? So we can say that industry classification, wherever the financial services column is equal to 1, we're going to grab that index. That's the financial services companies. So you see American Express, American International Group, Bank of America, Capital One, a lot of these different finance companies. Now that we know that, we can actually look at which companies are in the financial services. What are their distances between one another? Because we're interested in saying, are financial services companies more similar to one another, which we'd expect, or are they more similar to non-financial firms, which would be unexpected? So if we do this, we need to just make a few indexes of true and false values based on if we have companies within these financial services indexes. And then if we do indexing by it, we can now see the mean distance is much lower for the financial services companies than the non-financial services companies. As well, we might want to look between each combination of industries. So once again, we're doing iter tools, and we're going to take combinations of each of the industries, and we're going to try and see which industries are most similar to one another. So now that we have that idea in our mind, we're going to create a function. This function will take each of these keys and do exactly what we were doing before, finding average distance by indexing based on it. For finding industry distance, what we're really looking at is what is the difference between industry A and industry B in terms of their distances on average. So we want to find firms that are in industry A, firms in industry B, and we want to find all the different combinations of pairwise distances, and then we want to find what is the mean distance of those combinations. So that's why we're here looking for indexing and then finding in our distance data frame what the average distance is. So now we've initialized this data frame with all the different combinations like before, where we have our first column is industry 1, our second column industry 2, and now our third column is the average distance based on this formula we just defined. We'll get rid of the null values, and then once again we're going to do mirroring just as we did before. After that, we're going to say which ones are most similar, and when you do that, you see industry 1, consumer goods, industry 2, entertainment, has very low distance to one another. So we can kind of go through and we can compare, contrast which industries are really the farthest from one another. Now let's revisit financial services. Which industry is most similar to it? So we see financial services. This is interesting, entertainment. Now when we're doing this, it might not be an actually fair representation. There's biases that we haven't really controlled for. We haven't done any sort of term frequency, inverse document frequency normalization. So when we look at further examples in the next week, we're going to actually start to look at these kinds of normalization methods. So for now, just understand that there could be some sort of issues. Or maybe it's just that these companies actually are very similar. But then we see banking, artificial intelligence, telecommunications, and these are more of a typical fit for maybe a similar company to financial services. If we now grab the top industries that are similar to it, we say entertainment, banking, artificial intelligence, we can have this list, and we add in financial services, and then we actually pivot industry 1, industry 2, and distance from that data frame, re-index based on the top industries, and we have this pivot table now, which shows all the different similarity measures. Given these similarity measures, we can now plot this into a heat map, which is a visual representation of just how similar these different companies are. Now, I don't like the classic color scheme, so you can even add in your own color map. And now here you see a lot of these financial services companies are actually more dissimilar than the other combinations. So you see artificial intelligence and consumer goods, a much lower average distance. So it could be that financial services tend to have words that are very niche and not very common to all these other industries. Finally, you can just add annotations to get the numbers if you want. And that's the kind of final output of visualization of the average distances. Now that we have this 13F data, the question becomes, what is the value? Now this 13F can give us some really good insights into what different funds are holding. Now in this example, we don't have the entire universe, but The idea is still the same. We want to see what kinds of holdings are common across different funds, and we also maybe want to do some kind of statistics on exactly where those holdings are, maybe geographically or in terms of what kinds of funds hold what kinds of holdings. Now let's just take an example. For our first fund, we can get the stock holdings, the market value. We can just take the sum. That we can say is the fund value. From this we can also grab the state. So now we're building on that, and what we're going to try and create is a data frame which has for each state the total amount of fund value from our sample in it. So as you can see, for each fund we have the fund value and we have the state. Some of these are none. So these are ones where we couldn't actively figure out what the state was using our regular expression. An example would be there's one fund in this data set, and it's from London, and this fund's from London. So that one, there isn't actually an American state and zip code, so we actually can't use it. So these are kinds of things to consider when you're trying to apply these broad heuristics to figure out things like zip code and state. You might not even have a fund that has a state. What we can do for this is we say, first of all, we're going to get rid of any values where there isn't a state. Next thing we're going to do, we don't want any funds where there's 0 for any reason. We also are going to reset the index, and what we're doing here is we're grouping by the state, and we're getting the sum, so we're getting the total value in each state, and we also want to get the log of that value. The reason here is that we want to take out and see maybe there's skewing effects, and then if we use the log, it will at least attenuate some of those issues. Now, we're going to go back to Folium, and we're doing the state map now. So what we're going to do is have a very large zoom out, and we're going to center it around the United States. From here, we can actually map onto it the different states and the values. So we have to take from this URL, we get the JSON to actually put in. And now what we're saying is the columns are state and fund value. We're keying off the state, and we're also giving it a fill color, which is yellow to green. When we go and we add this to state map, what we get out is this. And from this we can see that a lot of the value is in California from whatever sample we took. Now you might be curious why it's California. There's many possible reasons. It could be the large California pension funds, for example. There are a lot of different examples of large investment holders that could be there. But that's for another day. Now, what we really also are interested in is, what does the log fund value look like? Because here we begin to see a little bit more of the description, and you see, yes, California is still the biggest, but now we see over here, all these other states look a lot more dense. We see a lot more value in there when we look at it from the perspective of log. So while we may have the majority of the money in California, it might be kind of biasing to only assume it's there. Now, let's create a master data frame with all the different holdings. We're going to deal with any sort of issue coming from if there's the same name on a fund by just combining them together. And from there, what we get out is the issuer, which is what the actual holding is, and then the fund up here, which is all the funds that hold it. And these are all the different funds in our data set. Now, why don't we see what the top represented issuers are, or the top represented holdings? We see Microsoft has 21 different funds that hold it. Johnson & Johnson 20, Apple 20, Pfizer 20. So this is good because we can start to see what are the most common holdings. Now the other kind of thing you might want to apply to this is see change in holdings. So let's say Apple, one period, there's 100 of the funds you're tracking that have it. The next period, there's 50. You'd be curious why 50 funds now no longer have it. We're not going to go into the differences for this course, but it's an important kind of thing that you can build off of and begin to look at. Something else. Let's look at the top 5 stocks. So we're going to go through and we're going to sum up and we're going to say what stocks hold the most value. It's Microsoft, Johnson & Johnson, Apple, Pfizer, and Pepsi. With this in mind, we can go through all the holdings, and we're going to find all those places where it's those top 5 stocks. We're going to stack it so that we can get it in a different kind of format. And then we have basically the stock, the fund, and what the holding is. Now, what we want to do is actually say for each state how much of the value of these stocks are held in there. So what we need to do first, we actually have to create a mapping from fund to state. So what we're going to do is make a data frame where we have the company name and the state as the 2 columns for each company that we have in our data set. And we're also going to say the columns are fund name and state. And then in case there's any overlap, we're just going to take the first state that's represented in the data set for a fund name. So you see now we have all these funds and we have the states. So what we can do now, we can join in this map. So now we have our stock, our fund, our holding, and what state is represented. And then we can drop NA, so we can get rid of anywhere we don't have the stock, the state mapping to it. Finally, we're going to do the same exact group by the stock and the state and find the holding. So for each combination of stock and the state, we will now have the total amount of holdings between all the different funds. Now, we're going to iterate through each one of these and create the exact same kind of map, except now we're actually going to look at it at a stock by stock by stock level. The idea here is we might want to see if there's some sort of geographical bias to any of these different stocks and who's holding them. So as you can see here, we have Apple, and we can see it seems like New York tends to have the most Apple. The New York funds, I should say, have the most Apple. You can see it with all the other companies. And now let's move on to actually looking at correlations between the different fund holdings. We'll create a binary version of this holding. So we'll say anywhere that it's greater than 0, so now it's true and false, but we'll convert it to an integer, so 0 and 1. We're going to call this the holdings binary. So 1 represents a fund holding that sort of issue. 0 represents a fund not having it. Now, when we do this, we can go through and we can say correlation. This will give us the correlation between the binary holdings. So if we have all the exact same kinds of stocks, we're going to end up seeing perfect correlation. And as we have less and less stocks in common, we'll see the correlation go down. Now, let's also do this, getting rid of the duplicates. So when we look at this, there's an obvious 1 across. That's because there's perfect correlation with one another. Just to clean it up, what we're going to do is we're going to actually get rid of that diagonal, and we're going to get rid of the bottom of the matrix, anywhere under this diagonal. And the reason we're going to do that is because we want to stack and we want to actually see what the most correlated funds are. But we don't want to accidentally have repeated numbers, because if you do this matrix, you're going to have a mirrored image. And we don't want to have those 1s because that doesn't mean anything. So to find the diagonal elements, we're going to first do this. We're going to get NP.indices, and this will return so for a data frame, it's going to return a 2-dimensional matrix that will essentially give us the row indexes and then columns, so it'll be column indexes. When we do this, we can say if rows is equal to columns, that is where we have row 1 is equal, the index of the row is 1, the index of the column is 1. That's a diagonal, as you can see here, here, and here. And we can say anywhere where the row number is greater than the column. So we're going to say anywhere where that's true, we're beneath the matrix indices, and we want to get rid of that. So either of these two, that's what this OR is, that's our new mask. And we're going to get rid of all of those. So with that in mind, what we're going to do is get the exact same thing. We're going to get the correlation, then we're going to mask. So we get rid of the diagonal, and we get rid of the bottom elements. And then we can just see right here, this is the head. So you can see that a lot of these under it are all erased now. They're not anymore in the data set. So we've gotten rid of the diagonals. We've gotten rid of the bottom of it. And now finally, we can see, after doing all of that, what the most common correlations are. And so this is an example of something that's interesting, is that we have this Metropolitan Life Insurance and we have MetLife Advisors, 98.5. Now, why do you think that is? We also have some of these other ones, and we might be wondering, what are the correlations among them? And why are they? Are they having a same choice? Do they have very similar holdings? Regardless, the main idea here is that we are looking into finding how these holdings coincide with one another. And this is just one way to look at it.
In the lab session, you learned how to extract 10K from the SEC website and process it textually. In this session, we'll focus on the competition section. It is actually a subsection of part 1, and it's not mandatory. Companies do not require to have a competition section, but many of them choose to do so. What is available through the competition section? Well, companies disclose their business environment, what segments of the markets they compete in, and typically they designate, they indicate which other companies they compete with in each of the sections of the market where they operate. We'll work on that section. Most of the studies that use corporate disclosure, they try to figure out information about the company disclosing the information. We actually take the opposite approach. We're trying to figure out the competitive state of a company, not by what the company is saying about itself, but rather what other companies are indicating with respect to that company that we're trying to assess. Specifically, we're looking into companies that designate another company as their competitor. The hypothesis here is that if many strong companies pointing at me as their competition, I am now in a very risky situation. If weak companies pointing at me, I should not be that worried. If no company designates me as their competition, I could be even more relaxed. The challenge here is, of course, to assess the competition states of any given company based on the companies that pointed at them as competition. It sounds like a very difficult problem to estimate simultaneously across all companies at any time period. However, luckily, Google had the same problem just a few years ago when they had to decide how to rank websites as a result of a search. And they used the PageRank algorithm invented by the two founders of Google to figure out exactly what we're trying to do here. How the standing of a website being affected by links that pointing at that website from other websites. If very strong website pointing at you, you probably have to be ranked high. But if no one pointing at you or very weak websites, then you have to be ranked relatively low. We do the same thing here with companies, and the links are equivalent in our case to a designation of a company as a competitor. So let's look at a very simple example. Imagine we had only 3 companies, A, B, and C. Company A is pointing at company B as their competition. Company B pointing at company C. But company C points both at company A and company B. So the question here is how to determine the strength of each one of the companies relative to the others. The way we solve these 3 equations is identical to the way Google ranks the web pages. Let's start with company C. It's being pointed at by company B. Therefore, the entire weight of company B is now assigned to company C. And that's the 3rd equation. Let's look at company A. What company points at company A? Of course, that's company C. But only half of the weights that company C has is now allocated to company A because company C also points at company B. So it has to split its weight. And that is described in the first equation. Now let's look at company B. It's pointed at by both company A. The entire power of company A is directed to company B because company A has only one link. But only half of company C's weight is pointing at company B because half of it was already considered when we calculated company A's equation. Now, one thing to keep in mind, just to make sure that companies which are not being pointed at will have some ranking, and to make these things solvable quickly, we consider a constant in each one of the equation, and we allocate the weights between the constant and the actual weights, that is, the actual strength of pointing. So if we solve these three equations, we get the results, which suggest that company B is the most central or the most competitive companies based on that very simple economy. And that's not surprising, because company B is pointed at by both A and C. Which one is the second? Of course, it's company C. And why it's more competitive than company A? Because it's pointed by a stronger company, that is company B. So company C now has a higher competition ranking relative to company A because it gets its strength from a stronger company. So now when we develop the machinery and we know how to simultaneously evaluate the competitive power across all companies, let's go to the data. So we collected the data from about 120,000 10Ks over a long period of time, covering more than 10,000 companies and close to 70,000 reports. Actually, about 60% of the reports include competition section. And then we do a very simple thing. We sort companies from the least competitive to the most competitive, and we divide them to quintiles, to portfolios. And then we assess the performance of portfolio with high competition ranks firms versus the low competition rank firms. And we see that this portfolio is actually generating excess return in addition to the market and in addition to other risk factors. And now the question is, how do companies make those returns? Is it due to companies that pointing at them from the same industries, or companies that pointed at them from different industries, across industries? And the results suggest that most of the power actually comes from pointing from other industries and not from within the industry, which is very insightful results if we think about disruption risk. So let's summarize. We're able to extract 10K information for thousands of different firms. We extract this information to assess competition risk and competition links between all the companies in that universe. We're able then to sort them into portfolios, choose the one with high competition rank, and sell the one with the low competition rank, and achieve abnormal return on average over more than 20-year period. In this session, we'll ask three questions. First, we'll ask, do local managers disproportionately hold local firms in their portfolios? That is, do they prefer to invest in firms that are located just next to them compared to the entire opportunity set that they could have invested in? The second question is, do local managers have better information about the local firms that they hold in their portfolio? If so, we'd like to investigate whether we could use this information in order to predict stock return. The information we're going to use in this session is based on fund holdings, and we'll show in the labs how to extract fund holding from 13F. We will also use geographic location of both fund management headquarters and companies' headquarters that are held by fund management. To proceed, we'll calculate the distances between each fund management headquarter and the headquarters of the companies they hold. For each fund management company, we'll calculate the average distance to identify the average proximity of the management company from the companies they hold. But we'll have to compare it to something. So we'll compare it to the opportunity set. We'll compare it to the average distance of the same fund management companies for the companies in their benchmark. That is, the companies that they could have held if they chose to. The difference between these two numbers are going to give us whether there's a preference for companies, for fund management companies, to hold their neighbors, companies that are located just next to them. So let's look at the results. Well, they're very convincing and highly significant. Indeed, fund management companies prefer to hold local firms compared to the firms that they could have held, which are on average located farther away from the companies that they actually hold. So the second question, if you remember, is whether they have access information, an information advantage by investing in local companies. So what the researchers have done here is something very simple. They split each portfolio of each fund management companies to two parts. One that consists of local firms that they hold, and one that consists with distance firms that they hold. And they actually see that the fund management company is actually being able to produce higher return in the portion of the portfolio that is actually locally positioned in close proximity to their headquarters. So that answered the second question. Fund managers have information advantage on local stocks. So the third question is obviously, can we use this information to predict stock returns better than we could do if we didn't have that information? And the answer for that is simple. The researchers looked at any given firm in the universe and ranked it based on the proportion that is being held by local companies versus distant companies. So they have this variable that they call local ownership. Now, when they regress these variables on future return, they find highly significant positive relationship, which means that locally owned stock overperform non-locally owned stocks. And we can use this information in our predictions exercises.
Actually build a network graph from this. The first thing we're going to do is we're going to say, look at Netflix. Now, by looking at the row Netflix, we can see which different tickers actually refer to it the most. So looking here, we can see the top 6 tickers. Now, we're going to think about this as building levels outwards from Netflix. Netflix is the center, and we're going to say the next 5 biggest connections are, we're going to go for the first outwards level. So he says first level is those 6, and now we have the source, the connections, and the target. All of them are targeting Netflix, and these are the 6 sources, one of them being Netflix itself. Now for the second level, we want to actually go through and do the exact same thing, but we can't redo and add new tickers that we've already seen. So we say if our value is Netflix, we're just going to pass over it. We've already put that into the level. Otherwise, we're going to do the exact same thing. So for each of these 5 nodes in the first level, we're going to find the 5 that link to them the most. And what this will do is we're going to keep recursively iterating. So from there, we get our second level. And now we can see all these other ones. And now the targets are those 5 that first were in the level 1. Finally, we'll do the exact same thing for the third level, and now we have a true graph. We can see that we've actually expanded out to 3 levels. Now let's work through the actual visualization, how to use NetworkX, the library, to actually build out this graph and see the connections. So the first thing we're going to do is initialize the graph. To add a node, you can say add node and then give it the title. And then we can actually just draw it very simply. So here we have it, Netflix. There's nothing else connected yet, but we're going to start seeing how all these connections play in. Next thing we could do, we could say, for all the nodes in the first level for target and source, add those nodes. And now we see. We also, just make a note of, are making this set in the node for loop to make sure that we don't actually repeat nodes. You see those 6 there in the first level. We can actually make connections like this. When we say add edges from, we can say add edge, and then that inner list is Netflix HON. So that's one connection. We can say Netflix Siri. That's another connection. We can begin to see here how the connections are drawn. Now, let's actually say add levels. But for this, we're going to say the edges are the source and the target lists, which we're getting from that first level data frame. Now you see, Netflix is in the center, and we're connecting out to the 5 other nodes. Now, we could also say, give me the first and the second level. And now, if we do the exact same kind of methodology, we see we've expanded 2 levels. And we can see that there's actually some crisscrossing now. And there's some where we actually have no other connections. It's just outwards, first level, outwards, second level. Finally, we could extend to the third level. And this is where it gets tough for the human eye to start seeing things. And this is where visualization can kind of have troubles. Now, there are other ways to actually visualize these better, such as having it be dynamic, where you can actually move around the nodes. Certain libraries have that as well as other programming languages, such as D3. And those kinds of libraries and their languages will let you play with it and let you see more actively. Of course, we're not going to cover those yet because they're a little advanced, but that's just for the future if you're ever interested.
In this session, we'll go over multiple application examples to determine how media can help in predicting financial market variables. Specifically, we'll look at variables such as trading volume. That's the trading activity that people actually do in the marketplace, rebalancing their positions or opening new or closing existing position. Then we'll try to figure out whether we can use media to predict risks. And finally, future stock returns. One of the first papers that tried to associate media and financial market activity is Antweiler and Frank in their Journal of Finance paper from 2004. They had access to about 1.5 million timestamped messages posted on Yahoo Finance, sort of social media activity designated for people interested in financial markets and specifically in stock trading. Their findings were strong. They found strong contemporaneous correlation between number of messages posted and the trading activity, the volume in the stock that were discussed. But the results could not establish causality. It was not clear whether people talk about stocks and then they trade them, or whether there's a market activity which then people chat about in these social network chat rooms. And that was exactly the starting point of the Journal of Finance paper from 2011 by Engelberg and Parsons. They directly addressed the causality question. What method did they use? they identify local markets with local media sources that serving these local communities, these local geographical units. And then they identify trading activity by individuals that live in these local communities. How they were able to do that? Well, they have access to really, really good data. First, they collected data from 19 local media outlets that serves, each one of them serves one of these 19 local communities, communities such as Pittsburgh and St. Louis. And then they have access to broker account data, about 70,000 individuals, broker account logs, including these individuals' addresses that then could be associated with the same 19 individual, with the same 19 local communities. So now they could test this hypothesis. Well, they looked at media coverage of companies by each one of these 19 local newspapers, and they observed the trading activities of individuals consuming this information in the local market. And they were actually able to establish very strong correlation between what people read, what stock they read about, and the activity that they generate in the marketplace in the same stocks. But they did not stop there. They also tested what happens when there are severe weather conditions. Why it is interesting? Because typically when there are severe weather conditions, snowstorms, hurricanes, then it's likely that the newspaper delivery is going to be disrupted. That is, people will not be able to consume this information that we saw affect their trading. So if information is not delivered to them, we'd expect to see less association between what the media is saying and how people react. And indeed, they found highly significant coefficient when they interact the local weather conditions with the local media coverage, which further strengthen the initial results. The next question is whether media can predict risks. My colleagues and I were actually very interested in this question, and we measured the abnormal media coverage for each of the stocks in the S&P 500 universe. Because media coverage is persistent, we actually had to predict, to have an estimation model for each stock every day of how much media coverage we'd expect it to receive. We then went and see how much media coverage there was, and the difference between the two is a proxy for the abnormal media coverage each stock receives each day. The hypothesis is very simple. Information provided about stocks beyond expectation help in resolving uncertainties and hence leading to reduced risk. We used various measures of risk. For example, we use implied volatility, which is actually derived from option prices. We use unexpected implied volatility, which is, first, we observed the forward implied volatility, what the market expects for the future implied volatility to be. We let time lapse, we observe the implied volatility, and the difference between the two is the unexpected implied volatility. We also use more traditional measures of risk, such as realized volatility and volatility premia, which is the difference between the volatility realized in the market minus the implied volatility that was expected. All the results suggest the same. Abnormal media coverage helps resolve uncertainty and therefore predicts lower risks. We saw that this uncertainty is being resolved over a period of about 21 days. But to make sure we didn't stop there, we repeated the analysis, this time not on stocks, but on foreign exchange, and we observed the same things. The more coverage beyond what you'd expect on foreign exchange, on currencies, so there's more information available, the less risk you'd expect for that covered foreign exchange rates. The next question is whether media can help predict stock returns, and more specifically, media coverage. So one of the first papers that looked at that was Fang and Perez in the Journal of Finance paper from 2009. They actually looked at information pertaining to stocks in the NYSE and the NASDAQ. The information was drawn for 4 major US newspapers: the Wall Street Journal, New York Times, the Washington Post, and the USA Today. They looked at, they extract information over 10 years, and essentially what they've done, each month they sort stocks into 3 portfolios. Portfolio of firms which receive no media coverage, then stocks receiving some media coverage but not a lot, and the third portfolio was the portfolio of stock that received a lot of media coverage. What they observe is that the portfolio with high media coverage stock underperforms the portfolio with firms with no media coverage. And the results are highly significant. Well, but that's not surprising. If we appreciate that people actually hold stock more, so they have portfolio that is long stocks, and they can only hold stocks that they actually recognize, they know about. They cannot buy something if they don't know that it exists. So then assets which are recognized, that have high coverage, tend to already be overpriced and therefore have lower expected returns. The next question is whether sentiment derived from media coverage could help predict stock returns. Shen, De, Hu, and Wang, in their Review of Financial Studies paper from 2004, addressed that question. They looked at information from the social media platform Seeking Alpha. This platform has about 1 million users, and about a third of them actually contribute content to the platform. They were able to cover about 7,000 firms, and what they've done was very simple. When a user had posted a short article or message about a company, they actually use exactly the same method that we covered last session and calculate the sentiment. Specifically, they use the negative terms in their calculation. And what they found that excessive use of negative terms help predicting future negative returns for the stocks that are being mentioned in the short post on this short article. This predictability period is over up to 36 months. But they did not stop there. They also looked at the responses of other users to the initial post by the initial user who published that small article. And they scored them using the same methodology by counting the negative terms in this post. And what they found was that in addition and independently of the initial message, a negative sentiment of the responses to that message also predict negative returns for the stock that is being discussed in this initial message. So overall in this session, we were able to demonstrate that media could be highly useful in predicting financial market variables. The variables we looked at were trading volume, risk, and future returns.